Today we're going to start talking about trig functions with acute angles. So the first thing we need to do is to recognize the triangle that we're looking at. It begins at the origin, it moves along the x-axis, some value of x, it moves vertically a value of y, and then ends at the origin. The angle that's created is a ray, and its measure is theta, some distance from the x-axis. So the x-axis is the initial side. This hypotenuse, or this ray, is the terminal side. Because we have created a right triangle, this longest side is the hypotenuse. The other terms we need to be familiar with is the term opposite and adjacent. Anytime we refer to opposite and adjacent, it is with reference to our angle theta. Opposite of theta means that it is directly across from theta. Adjacent to theta means that it's the ray that creates theta that is not the hypotenuse. Once we've identified the major signs of the right triangle, we can then talk about the three most common trig functions. The first one is sine. It's written S-I-N, but we pronounce that sine. The next is cosine, written C-O-S. And the last one is tangent, written T-A-N. We do not refer to these as sin, cos, and tan. We always use the terms sine, cosine, and tangent. These functions are ratios, and they are always equal to the same things. So sine is always the side opposite of theta divided by the hypotenuse. Cosine is always the adjacent side to theta divided by the hypotenuse. And tangent is always the side opposite divided by the side adjacent. The point P along the hypotenuse that created the distance of the hypotenuse can be located anywhere. So that distance doesn't matter because these ratios don't change, which is why we always say sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. We call this acronym SOHCAHTOA. It's the way that you remember which components of the triangle go with each trig function. Each of the three trig functions has a reciprocal function. They are secant, cosecant, and cotangent. So secant reciprocal, or secant is 1 over cosine. If cosine was adjacent over hypotenuse, secant is hypotenuse over adjacent. Cosecant is 1 over sine, so if sine was opposite over hypotenuse, cosecant is hypotenuse over the opposite side. And finally, cotangent is 1 over tangent. So if tangent was opposite over adjacent, cotangent is adjacent over opposite. A trig identity is an equation that involves the trig functions that's true for every value of theta. So the first trig identities that we're going to look at are the quotient identities. If you referred back to your definitions of sine, cosine, and tangent, we saw that sine of theta, we called it y over r, and we called cosine x over r. So quotient identities discusses what happens when we divide these. So if we did y over r divided by x over r, and we did what I like to call copy dot flop, so there's your copy, there's your dot, and there's your flop. These cancel. You end up with y over x. Going back to that slide, you would see that y over x is tangent of theta. So we can conclude that the sine of theta divided by the cosine of theta is equal to the tangent of theta. We can do the same thing doing cosine over sine. Remember that cosine is x over r, sine is y over r. We can copy dot flop. And we end up with x over y. Well, x over y is equal to the cotangent of theta. So, cosine over sine is cotangent. The next identity we're going to prove is a Pythagorean identity, and it's the most commonly used one. Sine squared of theta plus cosine squared of theta is equal to 1. Now, please notice that we use this notation sine squared of theta, cosine squared of theta, rather than writing sine of theta squared. This is not common notation. So make sure that you're writing like this. In order to prove this identity, we're going to imagine a right triangle with sides x and y and hypotenuse r. And we're going to use the Pythagorean theorem that x squared plus y squared equals r squared. I'm going to replace sine squared of theta and cosine squared of theta with y over r, quantity squared, and x over r, quantity squared. Extending the exponent, I get y squared over r squared plus x squared over r squared. I can then combine the numerators because there's a common denominator. When I do that, I get y squared plus x squared over r squared. Well, I know that x squared plus y squared equals r squared, so I can replace y squared plus x squared with r squared, but I have to keep my denominator of r squared. Now anything over itself is 1. So what we've done is we have proven that sine squared of theta plus cosine squared of theta is in fact equal to 1. Sine and cosine, secant and cosecant, tangent and cotangent are all called co-functions. Looking at this triangle shown, we know that the sine of A is A over C. That's also cosine of B. Tangent of A is A over B. Well, that's also equal to the cotangent of B. the secant of A is C over B, and that's also equal to the cosecant of B. So what this is saying is that one function of a given angle is equal to the cofunction of its complement. Remember that A and B here are complementary angles, meaning they add up to 90 degrees. So the sine of A is equal to the cosine of B. If you look at this chart down at the bottom, the sine of theta is the cosine of the complement of theta. And this is true for all the trig functions. Let's look at some examples. We have an acute angle theta in standard position, and its terminal side passes through the point 2, 4. I could sketch this really quickly. The point 2, 4 is here, and there's my angle. Here's my triangle. I have an x value of 2, a y value of 4. First thing I need to do is calculate the value of r. This is a right triangle, so we can use the Pythagorean theorem to calculate the value of r. Remember that r is the square root of 2 squared plus 4 squared. So r is equal to the square root of 20. And I can write that in simplest radical form. 20 is 2 times 2 times 5. That's prime factorization. Anytime a value is repeated, I can pull that value out of the radical. So r is equal to 2 times the square root of 5. Now I have a value of r. I know that the sine of theta is equal to y over r. So that's 4 over 2 square roots of 5. The cosine of theta is x over r. So that's 2 over 2 square roots of 5. And the tangent of theta is y over x. So that's 4 over 2. I need to simplify all of these. To begin with, the 4 and the 2 will cancel, leaving me a 2 in the numerator. So that's 2 over the square root of 5. There's a rule about not allowing radicals in the denominator. It's called rationalizing the denominator. In order to rationalize the denominator, you multiply that radical by both the numerator and the denominator. And you end up with 2 square roots of 5 over 5. For cosine, these 2's cancel, and you're left with 1 over the square root of 5. The same rule applies, so we're going to multiply by the square root of 5 over the square root of 5, and that's going to give us the square root of 5 over 5. And finally, we can reduce this to 2. So our values for sine of theta, cosine of theta, tangent of theta. For this next example, I need all 6 trig functions. My x is 3, my y is 4, I have to calculate r. So r, I know, is the square root of 3 squared plus 4 squared. That's the square root of 25, which is 5. So now, the sine of theta is y over r. That's 4/5. The cosine of theta is x over r, 3/5. The tangent of theta is y over x, 4/3. Now we will use the reciprocal identities, the reciprocal of each trig function. Remember that the reciprocal of sine is cosecant. That's 5/4. The reciprocal of cosine is secant. It's 5/3. And the reciprocal of tangent is cotangent. And that's 3/4. Here I'm given that the sine of phi, that's how you pronounce that, is 5/13. I need to find the cosine of phi and the tangent. Remember that sine is y over r. So 5 is y, and 13 is r. So now all I have to do is calculate the value of x. In order to do that, I'm again going to use Pythagorean theorem. I know that 13 squared is going to equal x squared plus 5 squared. So I've calculated the value of x to be 12. Well, the cosine of phi is x over r, so that's 12/13. The tangent is y over x. In order to do the next set of problems, we need to remember some special right triangles. The first is a 30, 60, 90 triangle. The side opposite of 30 is going to be what we call 1. The hypotenuse is double that value. So if the side opposite of 30 happens to be, say, 6, the hypotenuse is going to be 6 times 2. The side adjacent to the 30-degree angle is the square root of 3. So whatever value you have here, you multiply by the square root of 3 for this side. On a 45, 45, 90, the ratios are 1, 1, square root of 2, meaning that the two short sides are the same, and the long side is whatever that value is, times the square root of 2. In this example, I'm given a 45, 45, 90 triangle. What I know is that side C and side A have to be equal to each other. Now, if I look at the chart on page 558, I can see that the sine of a 45-degree angle is the square root of 2 over 2. Well, I know that the sine of A, in this case, is A over 12. And with the sine of A being 45, I can replace square root of 2 over 2 with A over 12. And I can solve for A by multiplying by 12 on both sides. These cancel. That becomes a 6. So A and C are both equal to 6 times the square root of 2. The last problem doesn't give me any angle measurements, but what I can see is that the shortest side is twice as long, or that is half the length of the hypotenuse. So when the hypotenuse is twice as long as the longest side, I know that this short angle has to be a 30-degree angle. The chart that's on page 558 are the most commonly used trig ratios for 30 degrees, 45 degrees, and 60 degrees. You need to have this chart memorized. That's it.